Great. Right. Good morning, everyone. Thanks for coming, first of all, despite the beautiful sunny day. And of course, today was like yesterday, attendance in the other room, summer again. Anyway, it's a real pleasure to be here at Sant'Anna, Hanretty, and Hanretty is fantastic, let's say, since he was here for us 15 years ago, roughly, I think, 20 years ago, 15 years ago, at the UI, when he was doing there his PhD in politics. He's moved back to his own country, the UK, and is now a professor of politics at Royal Holloway, University of London, where he's been head of the department that he stopped doing that job a couple of years ago, even more. He does party systems, elections, judicial politics, courts, regulation. He also does political methodology, and is often commenting also publicly on things such as British politics, Brexit, elections, and the like. For instance, for any of you who have studied, restudied Brexit, is the one responsible of predicting Brexit support at the constituency level. So if you want to see how Brexit is doing at the constituency level, you will be estimating support for Brexit also with the newly redrawn boundaries of the constituency. So, if you want to get new data on that, is the one maybe. And indeed, today is presenting a first version, first draft of his new book, which is indeed titled Generative Party Systems. So it's a brand new work. It's really at the edge of research in this area of political science. And once more, I have to say, it's really a pleasure to hear from Chris where research is going in that area. Let me also thank you for giving you the floor, Chris, Professor Giuseppe Martinico, who has kindly hosted your talk in the context of the Project Express 2 that is leading as a local host of this Horizon 2020 project, which is indeed investigating political developments in Europe, mainly, looking at how populism, illiberalism are changing the parameters of political debates and the constitutional order. And therefore, I think a talk on party systems is also very relevant vis-a-vis the project that Giuseppe is indeed leading here in Pisa in the broader context of this Horizon 2020 project. Without further ado, I've already spoken too much. I'm giving you the floor, begging you to speak not too far from the mic, unfortunately, sitting on there. Thank you, Chris, for being here.
Thank you very much for that introduction, and thank you also for the opportunity to present. It's wonderful to be here. I don't know how the organisers manage the sun, but coming from London is perfect. As Eduardo said, this is a book project which is 80% complete. If you have your laptop out and you like following things along online, I've listed the address of the slides at the bottom. Equally, if there's anything in this talk which is not clear to you and you have a quick question of clarification, please let me know. In my past life, I've worked with economists, and whenever you present with an economist, you can't get past slide 5 before some kind of interruption. But I wanted to start with a quote from the physicist Richard Feynman, who talked about our ability to create or simulate things. And the idea that if we can't create or simulate something, then we don't really understand it. And in general, political scientists don't do a lot of simulation. They don't do a lot of generating or creating. There are some attempts to simulate party systems in silico, try and play different party strategies off against one another. But these are generally described as being stylized, so not really very realistic. So I'm trying to improve on that today. And I'm going to describe a way in which we can simulate a party system with a given number of parties. We get that information to start with, and then we work out, can we work out a realistic set of shares for those parties and a realistic set of positions on the economic left-right spectrum? I think that is helpful because I believe that if we can simulate something, that's a kind of understanding. But I also believe it's helpful because if we can simulate these systems, then we understand more about certain emergent properties. So things like congruence, the distance between the average voter and the average party, or things like polarization, something which is coming up obviously in the context of the project hosting this talk. So I think it has two goals. First, describing something that looks realistic, and second, generating expectations about these other things. So to anticipate what I'm going to say, I'm going to argue that party systems are weakly centered on the position of the average voter, that parties repel one another. So if one party is already located in a position, it pushes other parties away. The parties, as we go from big parties to small parties, are increasingly eccentric or increasingly dispersed. And perhaps most importantly, that party positions are initially bimodal. If we think about the first party, it's never exactly in the center, but comes from one of two modes either side. And with those four mechanisms in mind, we can train some models which enable us to generate systems and see the potential impacts. So let's think about these mechanisms. And the first of these is the position of the average voter. So I've got my little left-right axis here, and I'm simply going to stipulate for the moment that the average voter in Australia is to the right of the average voter in Sweden. And no Australians or Swedes here, so I can say that, and no one contradicts me. Wonderful. So it would be kind of strange if the voters over in Australia got those parties over there with Swedish-style positions. So party systems have to depend in some way on the position of the average voter, but they might not depend exactly. And so as the average voter moves from right to left and from left to right, the parties might not follow them exactly. And so there's going to be some link there, but it's not going to be perfect. And so if we were to model that formally, we might say that the position of each party, which I've used the Greek letter theta to indicate, is going to be some intercept plus some coefficient multiplying the position of the average voter. And to give you some idea for that, that coefficient, that could go between 0 and 1. If it's 0, nothing happens. The average voter can move from left to right and the parties stay where they are. If it's 1, then if the average voter moves, the parties all move in lockstep. Each unit that the average voter moves, the parties move exactly the same amount. Or it could be somewhere in between. The parties could mostly move, but not follow the position exactly. And that's what you can see in that animation. So that's the first mechanism. We have to know where the average voter is. And the second mechanism is this idea of repulsion, of parties pushing other parties away. So I've stated that as clearly as I can there, but it might be more helpful if we just think, if we know what the position of the first party is, say if that big blue column is the position of the first party, and it's to the right of the average voter, indicated by that dotted line. If I just ask you, where do you think the next party goes? Well, you're probably not going to guess that it's another party on the right. Okay? It's probably going to be somewhere over to the left. And that kind of thing seems obvious, seems intuitive, but it's something that we have to build into a model. And it's something where we have to take account not just the position of the first party, but some kind of running average of all of the party positions. So if I didn't have just that first party, but I had a number of different parties all to the right, it would push the other party further to the left. If I didn't have just this first party, but I had a smaller party here, that might push the next party a little bit to the left, but not as much. So what I do is I calculate a running average. I take each party's share and multiply it by its position and divide it by the sum of all the shares that we've got so far. So it's just going along each party by each party, working out where is the average so far. And then I predict the next party's position using that information. And the worked example that I've got here is from the 2015 UK election, where we had the Conservative Party as the largest party. It was positioned on the right of the spectrum, so bigger numbers. And so that pushed the Labour Party away, and that brought the average system position down. And so when it comes to explaining the position of the third largest party, it's the system position so far that pushes the SNP a little bit over to the left. And again, if we wanted to model this formally, we could express that using another number which goes between 0 and -1. So in this case, if this number is 0, then parties just fall randomly. There is no dependence on any of the party positions that came previously. If this number is -1, then this factor acts like a mirror, and everything flips around the position of the 0 point, and we would expect the next party, the second party, to be as far away on the others. So these mechanisms so far give us some indication about where we might expect the next party to come. But one of the problems that we have is that some parties are just harder to predict. So as we go from the big parties to the small parties, some of those parties are going to be really hard to generalize about. By the time we get to those parties which just have a single seat, they could be anywhere. They could be, small regionalist parties. They could be radical right parties. They could be farmers, hunters, and fishers. We just don't know. And so, although we could make a good guess that the second party is going to be somewhere on the left, probably not on the right, by the time we get to the very last parties, we have to spread things out a whole lot more. And so again, if we want to formalize this, we have to make sure that the standard deviation, the spread of these party positions, it gets larger as the share gets smaller. So those mechanisms, the dependence on the position of the average voter, the element of repulsion, the element of increasing eccentricity, increasing dispersion, those all operate on the second to the last parties. I need something special for the first party. And here, I think a lot of us political scientists have been misled by work that suggests that parties, large parties, converge on the position of the median voter. That's very rarely the case. Parties don't fall into that position of the median voter as if it was some black hole that attracted them. In the data that I have, which I'll tell you about shortly, largest parties are always a little bit away from the position of the median voter. When you work with standardized positions, so something that has an average of 0 and a standard deviation of 1, they're around 3/4 of a standard deviation away. So they're nice and spread out. And that is another thing which you might think makes intuitive sense, but where turning it into a formal model is a little bit more difficult, because instead of having one simple bell curve, we don't have just one bell curve, we have two now. And we have to set the means of those distributions separately. So we've got one left-leaning distribution and one right-leaning distribution. So if we think of it as if we were trying to statistically model, I'm aware of stepping away, but I'm going to speak louder. If we were trying to statistically model my next footfall, right, there's 50-50 chance I start off with my left foot, and that's going to be one distribution. 50-50 chance I start off with my right foot. But no one would ever try and model the footfalls, imagining I land right? That's just not the right way to approach it. So although I talk about this mixture model that we need, and although it's a necessary formalism, hopefully the idea itself should be somewhat intuitive. So I've told you about some mechanisms, and I've given you some formalism and some parameters that we can adjust to say how strong those mechanisms are. But what I haven't done is to give you any way that we can learn about these parameters or turn these mechanisms into some way of generating systems. And that's where I need some training data. And as you may know, there are lots of different sources of data about party positions out there, and they differ in terms of their scope, the number of countries that they cover, and the period that they cover. So I've tried to combine these as best I can. And I've tried to combine them, again, trying to standardize. So all of those things on the left-hand column, some of them are measured on 0 to 10 scales, some on 1 to 20 scales, some on -3 to +3 scales. I've tried to standardize them so that everything has an average of 0 and a standard deviation of 1. But I told you, I'm not just trying to understand party positions on their own, I'm trying to explain them as a function of the average voter. And here's where things get a little bit tricky. So if I ask you about an election study that you've probably not studied because you're not Australian. What do you think the position of the median voter on a 0 to 10 scale was in this particular Australian election? It's not a trick question. Non sto cercando di ingannarvi. 5, yes. Okay. Second question. Different election. What do you think the answer is? 5 and 5 and 5. So, two possibilities here. One, the average voter in lots of different countries always has the same position. A miraculous discovery for political science. Two, people use the scale in different ways. And it's this possibility that I'm betting on. And so if I already have information on party positions, I can use that to reason about how people are using this scale. So I might have a measure of a party position, and I think it's a 0.6. And I go to my respondent, and they say, oh, for me it's a 6. And then we do another party, and I think it's minus 0.2, and they say it's a 3. If I have that kind of information, then if they tell me that they themselves, that they are a 5, I say, well, okay, you're probably some distance between those 2 points. And again, we can reason through that in the case of individual examples. But I've tried to do that systematically for about 300 different election studies. I've tried to use a multi-level model where we've got lots of respondents giving us judgments on multiple parties. I know where I position them. They tell me where they position them. And I try and work out how they've used the scale. So each respondent is allowed to use the scale in a slightly different way. And that allows me to get some estimate of the average voter's position. So I have information on party positions. I have information on the position of the average voter. Now, I'm well equipped to estimate all of those parameters that I told you about. And so I apologize for the size of this table, but I'm just going to show you some particular things which are important. So if we think about the position of the average voter, I told you it could be anywhere from 0 to 1. 0, no movement. 1, perfect movement, perfect symphony. And it's quite close at 0.89. We talked about the repulsion parameter. I told you it could be anywhere between 0 and minus 1. 0, no reaction. Minus 1, perfect mirror image. And here again, we see it's quite close to that minimum. So quite close to that mirror image world. But there is one other thing which I didn't expect when I started out, and that's a shift rightwards. So it turns out when you control for the position of the average voter, the parties that you get tend to be shifted a little bit to the right. So there's what we might term a right-wing bias in lots of different party systems. So now I've told you about the data, and I've used that data to estimate some parameters. But that doesn't mean that I can generate the system from scratch. I've just learned from actually existing systems. Now we need to generate. So if we think about a particular system, and suppose I tell you that this system has 7 seat-winning parties, and ask you to make a guess about the seat share of the largest party. Well, it can't be lower than That should say 1/7. I've got a fraction which has gone missing. So that 1/7 is our lower bound, because if it had less than 1/7, then with 7 parties, it wouldn't be the largest anymore. And our upper bound is 1. So how can we make a good guess? Well, Tagbera and Alec have suggested that what we can do is we can take the geometric mean of those two bounds. So not the arithmetic mean, not 1/7 plus 1 divided by 2, but 1/7 times 1, and then take the square root. And they suggest that that gives us a nice set of estimates for the size of the largest component, which in this case is a little under 40%. But the beauty of that logic is that we can repeat those same steps for all of the remaining parties. If we think about the second party, well, we've got some remainder there. That's 1 minus the seats that we've already allocated. And so we've got another lower bound and another upper bound. And we can repeat that logic. And now we guess, well, maybe the second party has a size just bigger than a quarter. And we do that for each of the parties in turn until we have a nice set of party shares that add up to 1, subject to the condition that there are 7 parties in total. Now that gives us a point prediction, a single number. But if I tell you this party system has 7 parties, it's very unlikely it's going to be 37.7, 25.6, and so on for all of those party systems. We need to make this probabilistic. So in previous work with Dennis Cohen, I've suggested a way where we can get a distribution of shares. So what I'm doing here is flipping the logic. Normally, we would think that parties adopt positions and then people vote for them. That is how it works in practice, right? But what I'm doing here is the other way around. I'm saying, let's take some distribution of seat shares or vote shares and then work out what party positions would make sense given those shares. So it is an example of what we might call an inverse problem. And it's a strategy which has worked before because one of the leading texts on electoral systems, Sugar and Tagliapera's Votes from Seats, argues that if we want to explain distributions of vote shares, we should start by explaining distributions of seat shares. That too is a little bit crazy because in practice, people vote and then we allocate the seats. But they're saying, actually, it's the seats that are a bit more constrained. So we need to reason about them first and then work out the possible distributions of votes. And then we get onto the question about whether any of this is realistic. Now, for reasons of time, I've cut some slides where I was going to present you with some fake systems and ask you to guess. So there's no audience participation today. But recently I went to the Elections, Public Opinion and Parties conference in the UK and I asked some attendees if they could guess whether certain systems were real, part of my training data, or fake, ones that I generated myself. And if they had been guessing by chance, then they would have got 50% correct. They did slightly better than chance. They got 55% correct, but it wasn't statistically significantly different from chance. So I'm going to take that as a sign that these things that I can simulate are good enough that they can fool some political scientists some of the time. So I'm pleased with that. So that's one of my objectives, but the reason I'm doing this is to reason about some of the effects. And so in the book, I'll be looking at these 4 things. So the system position, how far left or right is it? Congruence, so the distance between the average party and the average citizen. And then a slightly different thing, the distance between each citizen and the party that's closest to them. So not averages, but distances for actual real people. And then this question of polarization. And so in the book, the approach that I take is to start just assuming a very simple model that party positions come from a standard normal distribution, that regular bell curve distribution, work out the implications of that, and then reintroduce some of the mechanisms that I've just described to you. And I do test it on the data, and I don't think this is entirely circular because there has been some abstraction that's going on. So if we think about the system position and where it might be, if we just simulate some really boring data, on average, we're going to get a system position which is centered on 0. But in any particular case, the system might land far from 0, just by chance. But that's going to get smaller as we add more parties. It's easier if I visualize it. So in this left panel here, you've got some simulations where all the parties are the same size. In the right panel, you've got some simulations where the parties follow this Tagapera-Alec distribution, and where they have different sizes, and where I'm plotting using the effective number of parties, which is a kind of summary statistic, which is the number of parties that you would get if you made all the parties, if you manipulated their shares so that they became equal once more. And you can see that the average is 0, but the red lines, which show the 25th and 75th percentiles, they start quite far and come closer. As we add in some of the elements that I talked about, if we start with repulsion, that has a slightly counterintuitive effect. If I am here and I push people away, that moves that other party further away from the center. But it means that our two positions taken together are quite close to the center because we spread out a little bit. So when you average our positions, it ends up converging on 0 quicker. I don't know how well you'll be able to see this, but here are some simulations that change how much parties repel each other. And you can see that the blue dotted line, which is perfect repulsion, converges on 0 quicker. When we add greater eccentricity, that slows that rate of convergence, so it undoes some of the effects I've introduced. But what's really strange is when we add in that initial bimodality, when we make the system position start off in 2 different points. So remember, thinking of starting on the left foot, thinking on starting on the right foot. Here's where you get this kind of freak occurrence up here and down here, where there's just one party, before the system converges a bit. It actually gets a little bit more eccentric as we go out to the far right. There are other things that I'm not plotting. So things like the intercept, which pushes all of the positions of the parties to the right, and the position of the average voter, which will shift things. Not all of those impacts carry through on the way. So the repulsion tends to mess up some of the impact of the average party position. And so that means some of these effects are slightly smaller. But what I think is most helpful is if I give you the graph. I'll show you what it looks like, and then I'll come back and say how it looks. So this is the results from a model which is estimated on data, so it's not just a simulation, where there are two components. One component where the party system starts off on the right, one component where the party system starts off on the left. And as you might expect, if the party system starts off on the right, the system position, bigger numbers further to the right. As we add more parties, the system position comes closer to the center. So there's that element of convergence. The system position becomes less extreme. But if we start off on the left, well, for a start, the intercept means that the system doesn't start off very much on the left at all. And as we add more parties, it gets further to the right and converges with a kind of slight right view. And in practice, that's done through a nonlinear model where we've got some overall shift, which applies to all parties. We've got a peak, which in this case is where the right-leaning component starts off. And then a nonlinear term, which shows how this curve changes as we add more parties. Because in all of the simulations I showed you, I never got straight lines. I need some kind of non-linear effect here. And the good news is that now that we've worked through some of those steps for the system position, it's much easier to understand congruence. Because that's just the difference between the system position and the position of the average voter. But what is important to note here is that the level of congruence depends on where the average voter's position is. So here, I've got 6 panels with different average voter positions. In this top panel, top left panel, the average voter has position -0.5, so they're on the left. And for them, things are pretty bad. The average distance, when we turn the number of parties right up to 12, is 0.3. In the bottom right, or this bottom row here, I've got average voters on the right, and they have a much better time of it. For them, the distance is 0.6, 0.7. So the first insight is that the congruence of the system isn't just something that we know from the number of parties, it's something that we have to know the position of the average voter. In these diagrams, you'll see 2 lines for the blue line for when the system starts off on the right, the red line for when the system starts off on the left, and the grey line is just the average of these. So usually, adding more parties brings congruence down. It makes the distance from the average to the average small. But the slope of that line again depends on where we start. So if you're in this case here, where you've got a very right median voter, the slope of that line is not very steep at all. Whereas for someone like here, just slightly to the right, the slope is much steeper. So we have some complicated non-linear dynamics going on. The key things are that congruence depends on the position of the average voter, and so too does the effect of adding another party. I'm going to skip over the distance to the nearest party in interests of time and move on to talk about polarization. And again, we can repeat the same logic. We start with something simple and we add the complexity back in. So if we suppose that we're back in a very simple world where party positions follow a standard normal distribution, nice bell curve, and suppose that we measure polarization as the standard deviation of party positions. And in effect, that's what a lot of measures of polarization are. They're weighted standard deviations. Well, as we add more parties, we get up to infinitely many parties, then our measure of polarization should reach 1. Because this just here is just a shorthand way of saying a normal distribution centered on a mean of 0 with a standard deviation of 1. So if you've got a lot of parties, polarization is going to be at its maximum. If we have just one party, well, either the standard deviation is 0, right? How can you have any spread of points when you've just got 1 point? Or it's undefined. So we're going to see a pattern which goes from 0 to 1. And if you did in stats classes, there might be something that your lecturer mentioned about how when you've got a small sample, you need to correct for the sample variance. This is something known as Bessel's correction, and it gives a particular shape for the curve connecting the number of parties and polarization. It's a curve which looks like this. So strong increases as we go from 1 to 2 parties. And then, in effect, it tapers off as we add more and more parties. And the party system slowly reaches its maximum polarization of 1. I say the maximum. In practice, there can be cases above and below. This is the maximum long-run average. If you're looking closely, you'll see that there are 2 curves here. One is for polarization at the level of seats, one for polarization at the level of votes. And you'll see that the vote level polarization curve goes up sharper earlier. So the vote winning parties are a bit more polarized than the seat winning parties. But that again shows some of these nonlinear dynamics that are at play here. So I've tried to argue that we can generate party systems by starting with generating some shares and then working out what positions would make sense given those shares. I think, based on my opportunity sample of these conference attendees, that these simulations are realistic in some sense. And I'm trying to use them to generate expectations about these properties of the party system. And so if we are to reason about the effect of adding an extra party, well, that can shift the system position to the left or the right, depending on how the party system started off. Adding an extra party will improve congruence, so it'll make that distance smaller. But the effect might be quite small if you already have a lot of parties there. It will improve distance to the nearest party, which I didn't talk about, but it will come at the cost of increasing polarization. So if you believe that polarization is per se a bad thing, then you can't have all good things all at the same time. I phrase this in terms of adding an extra party. It might make more sense sometimes to think of taking some parties away or reducing the number of parties. So you'll be aware that the Netherlands had their election last week. There was a very, very large number of parties which got seats in the Tweede Kamer. And one question might be, if the Netherlands had a threshold, if parties needed 4% of the vote to get any seats, if there are fewer seat-winning parties, how would that affect some of these things that we care about? How would it change congruence, how would it change distance to the nearest party? In brutal terms, would people be more pissed off if the nearest party to them was much further away? And my answer is to say, well, probably not, because they have a lot of parties to begin with. I mentioned that this is an ongoing project. All of the models and the trends that I've shown you come from simulations and observational data, but there are some systems where we've got national thresholds of representation, which mean that we can compare what happens if a party just gets seats compared to if a party just loses out. So we can say, if this party, which got 4.01%, if it just got 3.99% and I gave their seats to another party, how would people feel? Would congruence be affected? Would the distance to the nearest party be affected? And so what I plan to do is work on some of those cases and see whether the predictions from observational data match what happens in reality. And in particular, given that I expect these heterogeneous treatment effects, I expect the effects of adding or taking away a party to be different depending on the number of parties already there. Everything that I'm talking about applies to the party system and not the governmental system. And so often when people are suggesting things like national thresholds or electoral systems that reduce the possibilities for parties to win seats, is because they think that improves governability. And I'm not talking about that because my book is already too long. And in particular, I find it really hard to talk about government positions. I don't know if anyone here works on cases of minority government, but minority governments are always a real head scratcher because you never know, is the position of the government the position of the party in the government or that party plus its legislative support? But hopefully, I'm making some kind of contribution to the idea that we have to trade off some of these things and making some of those trade-offs a little bit more obvious. So that is going to be all that I have to say. I'd be very interested in your reactions, particularly if your reaction is, oh, I hate this. So yeah. Yes. Stop the recording.